Hi, Neil Turok. Thank you
Hi,
so much for joining us on Conversations at the Perimeter.
my pleasure.
So I have to say, I've always enjoyed when I've had the opportunity to talk to you over the years. And one thing that I find particularly impressive about your work is that you have such a deep understanding of the big picture and the goals of fundamental physics. I think this is particularly difficult for researchers like me that can maybe get a bit lost in technical difficulties and calculations. So I want to start with a very big picture question.
Okay.
How would you describe the state of theoretical physics research today?
It's very interesting. It has grown into a very large field. There are tens of thousands of researchers around the world. At the same time, I think it's diversified enormously. The part of it which I'm most fascinated in is the fundamental understanding of the universe, be it on very small scales, as in particle physics, or very large scales, as in cosmology. And that part, I would have to say, has been, on the one hand, benefiting from incredible observations. On small scales, we have the Large Hadron Collider, most powerful microscope ever built, showing us what subatomic particles look like. And on the large scales, we have data showing us the whole visible universe with exquisite precision. So it's definitely been a golden age in that sense. But on the more theoretical side, I'd say the picture is more mixed. Since I started in theoretical physics in the early 80s, there have been great hopes about a number of programs of research: grand unified theory, supersymmetric theory, string theory, supergravity, M theory, and so on. And I would have to say that these have not yet panned out. It's very striking that there is not yet a single prediction which has been verified from any of these frameworks. So from my own point of view, on the one hand, you can, wring your hands and say, why hasn't theory been more successful in the last 40 years? All the theories we've verified are essentially rather old theories. Einstein's theory of gravity, the Higgs theory of the Higgs boson, and the Standard Model have been verified with more and more precision. But the newer ideas haven't panned out. So you can feel rather upset and disappointed about that. I don't. I think what's happening is that nature is speaking to us and telling us that he or she is simpler than we expected. Because what these observations reveal is a striking minimalism. We don't find any more we have not found any more particles in probing the universe at very high energies now at the Large Hadron Collider. And on large scales in the universe appears to be more or less as simple as it possibly could be, and still give rise to galaxies and stars and the structures we observe. So this is tremendously exciting because I think the simplicity indicated by the observations is, I believe, pointing us to new principles. And those principles will be deep and universal and highly predictive and highly constraining. And they will constrain the universe to look something like what we see. So whereas you might naively expect the universe to get more and more complicated as you go to bigger scales, the opposite seems to be true. And that I find extremely exciting because it means that maybe indeed we are the scales we live on and we operate on are perhaps in some sense the leading edge of complexity in the universe. The universe is much simpler on small scales, much simpler on large scales, and that helps put us in context. And maybe if we understand the big picture, the universe on very large scales, we will somehow understand where we sit in the universe. And I'm particularly excited about our recent work addressing the Big Bang. This is the most profound puzzle in all of physics, how everything emerged from a point. And I think over the last year or two, we've really started to make sense of that. And again, it indicates our new understanding is that the Big Bang is actually quite simple. It's not a arbitrary or chaotic or random process. It's a very precise, if our theoretical ideas are correct, it's a very precise boundary condition for the universe, and a highly principled boundary condition. And if so, then the universe becomes much more comprehensible in its entirety.
And as you said, many other researchers work on more complicated theories that are not embracing minimalism as much. Why do you think others tend to stray away from these simpler ideas?
I think, we're all trying to follow the example set by Maxwell with Maxwell's equations, or Dirac with Dirac's equation, or Einstein with Einstein's equation. These are tremendously principled, economical, mathematical equations which govern a bewildering variety of phenomena and are extremely predictive. So we're all trying to emulate, these highly successful theories we base our current theories on. But I think what happened is that particle theory over the last 50 years, maybe longer, got into the habit of always postulating new particles. And to some extent, this was natural because every time you built a new accelerator, you discovered new particles. And so this just became the norm, is that, we expect once in a while to add a few new particles. And the hope arose that by adding these new particles, at some point we would actually simplify the picture. So in grand unified theories, for example, you try to make sense of the pattern of particles around us by adding some more particles, and in such a way that the whole unified. And that habit sort of persisted. But it generalized. So instead of adding particles, people added extra dimensions of space, and extra objects. So there were strings in string theory, and membranes, and higher dimensional structures, which were added to these theories, all in the hope of sort of unifying this in a principle. However, the principles were somewhat lacking. So string theory, notoriously doesn't really have a clear conceptual foundation or principle in the same way that Einstein's theory of gravity had. In Einstein's theory, the conception was that you have curved spacetime, and this curved spacetime tells matter how to move, and in turn, the matter tells the spacetime how to curve. That's how John Wheeler famously described it. And those words, besides being very beautiful, they capture a concept of how the physical world works, which is very intuitive and very powerful. And when it's translated into mathematics, it becomes highly predictive. But string theory has lacked such principles. And it's been more a question of sort of follow your nose. And when you come across some phenomenon, you sort of tweak the theory, or you adjust your interpretation. And in particular in cosmology, quite a popular endeavor in string theory has been to try to picture the universe as if it was what's called an S-matrix. An S-matrix is something used to describe particle collisions. Things come in and things come out. But I think the way the cosmos works seems very, very different to an S-matrix. There was at least in the part of the universe we can see, there was a starting point, and there's this finishing point, which is dominated by the energy in empty space, the cosmological constant, sometimes called the dark energy. And so I think trying to shoehorn the universe into a preconceived picture, which was designed for particle physics experiments, to me seems, a sort of search for a principle, but not one that's particularly likely to work. So I think people have been trying to find principles which are economical and powerful and will explain lots of things, but to a large extent, those principles don't seem to be the right ones. And as I say, the enormous simplicity of nature is hinting that there are principles to be discovered. And yeah, I'm hopeful that we're beginning to get on the right track.
I've heard you say that a key ingredient in doing this work is having a lot of dialogue between theorists and experimentalists, but this is not always easy to do. And I think there tends to be a bit of a divide between these areas of research. So how do you think we can improve this and have more effective collaborations between theorists and experimentalists?
Well, I think it's difficult because both theory and experiment are very technical. When I started as a PhD student, it was very noticeable that the theorists where I were in Imperial College had their own seminars and the experimentalists had their own seminars, and they generally never went to each other's seminars. So the high level of technical complications in both aspects of science mean that people don't have time to often to interact much with each other. And that's very sad, because I do believe that theoretical physics should be, at its most exciting and most effective, should be connected to observations. And there's been an increasing sort of divergence of so-called pure theory from observations, and even a sort of philosophical justification by saying, oh, well, if we know our theory is right, for mathematical reasons, we don't really need to pay attention to the observations. And I'm very critical of such point of view because I think you can really easily go wrong in your mathematical assumptions, and very quickly just diverge from anything to do with reality. You need to keep one eye on the observations. It may not be in, very much detail. You don't need to get involved in experiments or data analysis or whatever, but you need to pay very close attention to, major observational results if you are to actually build a successful theoretical physics framework. So I think the field does need a bit of a reset. It's particularly important for students to sort of appreciate the wonder, the sort of miracle that theoretical physics is, that when it does connect to reality, it's quite magical. And I think the students who don't pursue that or aspire to that are really missing out on a lot. That one should, never forget that the real magic in the subject is when it connects to observations. And these observations are extremely fundamental. I mean, the universe, we know things about the universe, that the fact that empty space seems to have an energy, the cosmological constant, that's very profound. There are ideas, again, for interpreting the meaning of that. What is this stuff in empty space? And then we have the dark matter. Very good observations showing us that most of the matter in galaxies doesn't interact with light. And we have some very interesting candidates for the dark matter, some of which are very minimal, like neutrinos. We know neutrinos exist, and it's a very simple and natural idea that one of the so-called right-handed neutrinos is the dark matter. And the exciting thing is that hypothesis is possible to test. Within the next 5 years or so, people are projecting that through observations of galaxy clustering, one can actually detect even very tiny light neutrino masses. And if one of the right-handed neutrinos is the dark matter, and if it's stable, then it follows as a consequence that one of the light neutrinos is massless. And that should be possible to confirm within the next 5 years. It's very, very challenging work for people doing the observations and modeling, a lot of computational modeling to understand how the light neutrino masses affect the clumping of matter. But so far, the predictions are that we with the anticipated accuracy of the measurements, we should be able to tell quite definitively within 5 years or so whether the light neutrinos are massless. And if that is confirmed, it will be a very strong indication that we're actually on the road to understanding the dark matter. Mm-hmm. And then there are other things like the fluctuations coming out of the Big Bang. These take the form of quantum fluctuations in the vacuum, which is a very profound phenomenon that the quantum fields we observe, like the electron or the photon, all the other fields in the Standard Model, have fluctuations in the vacuum. And these are very paradoxical and strange, have very strange properties. For example, that if you add up all the energy in these vacuum 0-point fluctuations, it's infinite. And that doesn't make any sense because gravity couples to energy, and gravity would see that infinity. So for decades, we've been sweeping this under the rug and pretending it's not really there and so-called renormalizing it away. And this is this is not a good state of affairs because it means we do not have a physical picture of what's going on in the vacuum. And again, these new developments, some of which I've been involved in, are pointing to resolution of these questions, so that by modifying the vacuum of the Standard Model in a certain very precise way, you can cancel this energy divergence and, in fact, protect some of the deep symmetries in the Standard Model, one of which is called local scale symmetry. So, it's a surprising fact that a photon of light is pretty much the same as a photon of X-rays or radio waves, and they're all just scaled up or down versions of exactly the same thing. And that's a very deep symmetry of Maxwell's equations, that it's so-called scale invariant, and even more than that, it's locally scale invariant. So you can change the scale differently in different parts of space and time, and the equations remain the same. Why is that such a deep symmetry? Well, to describe the Big Bang, where everything came from a point, if all the material in the universe was insensitive to the overall size of the universe, as it is for Maxwell's theory, or actually for Dirac's theory as well, then the stuff in the universe doesn't know about the size of the universe at all. So even though from our point of view it all shrank to a point, the stuff of which matter is made doesn't see the so-called singularity. And this makes the singularity possible to model mathematically and to really understand, and to understand this boundary condition I mentioned at the Big Bang. So I think these principles, in other words, trying to deal with the vacuum energy infinity or divergence, trying to deal with the Big Bang singularity, these are really pointing us to the right principles which will explain the universe on large scales. And the thing I'm most excited about recently is that using these same principles, we've been able to calculate the fluctuations we now see in the cosmic microwave background. And amazingly, the numbers come out correct. We get the right size of fluctuations, we get the right spectrum without any free parameters at all. And so, this is early days, but it's a very exciting framework which may end up explaining the universe and connecting it to the fundamental physics of particles in a much more precise way than we ever thought was possible.
And is this something that you have been working towards your whole career, trying to work on these very simple models with very few free parameters? Or would you say this is something that you've been exploring more recently?
Essentially, I have been working with the same motivation for my whole career. I've always chosen to work on testable theories even when most people don't. And so as a student, I was very fascinated by an idea of my professor, Tom Kibble, that there would be cosmic defects in the universe. This was actually a consequence of grand unified theories. And what was exciting about it is if grand unified theories were correct, and if these defects had formed as they predicted, we would be able to see them. And so I spent a lot of time trying to calculate what they would look like, what observations would detect. And in the end, we disproved the idea that these defects gave rise to galaxies, which was one of the popular theories of the 80s. And I spent a lot of time trying to, calculate precisely what the predictions were. And then when the experiments came along to check, they just proved those theories wrong. So I was very fortunate to work on theories which could be proven wrong. Then when string theory came along, like most other people, I was very excited. Maybe this is a unified framework that really will explain everything. It's a theory of everything. And I did my best to try to reconcile string theory with cosmology. So we made a model of colliding brains in extra dimensions. And I would say at that point, I was beginning not really to believe. I didn't necessarily believe this framework, but I thought it was an interesting exercise to create a rival, a competitor to the most popular theory, which was called inflation, and hopefully one that was less adjustable and more connected to very fundamental physics, as string theory was, quantum gravity and so on. But I think the realization slowly dawned that, this whole framework was too complex. Especially as the observations have become simpler and simpler, and the kind of signals you would have expected from inflation have progressively gone away. So one of inflation's predictions was that there should be very long wavelength gravitational waves created as sort of aftershock of this burst of expansion in the beginning of the universe. And you could see these long wavelength gravitational waves through observing the polarization of the microwave background sky. And the measurements finally became accurate enough to see this effect. Initially, they claimed they had seen it. And so all the inflationists were very excited and thought, this is verification, including Stephen Hawking, my friend Stephen Hawking. Bet me in public that, we had a bet. I had bet they would not see it, and they now claim to see it. And so he wanted me to pay the bet, and I said, all experiments require confirmation, and there were reasons to doubt this experiment. In the end, the experiment turned out to be wrong, and now what's happened is that the latest experiments see nothing. And within 5 years or so, the upper limit on these gravitational waves is going to get so low that I think most people, most sort of relatively unbiased people, will draw the conclusion that inflation probably isn't the way to go. So that's really exciting. The precision of the experiments has got to the point where, large numbers of popular theoretical frameworks are now under severe pressure. So in the interim, all these things influenced me a lot. But I think especially when I was working at Perimeter, and I had the responsibility as director of sort of deciding which fields were worthwhile to invest in, that made me look very critically at the whole field of theoretical physics and try to assess, where the best prospects were. And of course, that influenced my research. And so when I left as director and I went back to full-time research, I was very determined to focus on theories which I sort of genuinely believe are promising and have a chance of providing very large explanatory power. And so that's what I'm working on.
Mm-hmm. And I know you've said that a lot of the work you're doing now relies heavily on some ideas introduced by Stephen Hawking, who you already mentioned. Can you say a little more on that?
Yes, I was very fortunate in many ways to know Stephen Hawking. When I was an undergraduate, I went to his inaugural lecture called, very provocatively, Is the End of Theoretical Physics in Sight? And it was sort of a lecture full of jokes. And at the end, he concluded it was in sight. And I was worried I'd missed the boat. They'd sorted everything out. It was supergravity was the answer. And that was that. But it proved to be over-optimistic. And then later I went back to Cambridge as a professor and made friends with Stephen, and we wrote several papers together. But what's special about Stephen is he had this, he was extremely adventurous. You know, at the time he started thinking about quantum gravity and black holes and how they radiate and the thermodynamics of black holes. You know, that was far ahead of its time. But his ideas were so deep, they have influenced the whole field for decades. And the way I think we're still struggling to understand what they mean. And he was too. We still don't really know what the entropy of a black hole means exactly. We think it's to do with how many different ways there are to make a black hole, but we still can't quite put our finger on it, on exactly what it means and how it's compatible with all of the rest of physics. But in our very recent work, and this is with Latham Boyle at Perimeter, we've developed Stephen Hawking's concept of entropy, gravitational entropy, to apply to the universe, the whole universe, and that's been really surprising. And in the course of that study, I've come to the conclusion that Stephen himself underestimated the power of his own ideas. Okay. So he developed the idea of entropy, of gravitational entropy, entropy of black holes, entropy of the universe. He never succeeded in calculating it for the universe, as we now have. And so he tied his ideas to inflation. You know, inflation, sort of, to put it bluntly, was the sort of ragbag of models, thousands of different models of inflation, all of them sort of tweaked and adjusted and with lots of assumptions to sort of fit what we see in the universe. And my current understanding is you just don't need it. You don't need to tie Stephen's ideas of gravitational entropy to inflation. Just take them as they are, apply them to the real universe without any extra particles or fields or inflation or anything. And they already explain why the universe is big, smooth, and flat. In themselves. And so that's been very exciting, is that I think we found that Stephen's ideas are more powerful than he suspected. And there are still questions about exactly what it all means, but it looks like they can explain the structure of the universe without any additional input. And then the other thing in what we're studying, you see, Stephen's ideas were very paradoxical in many ways. So he said a black hole, which only has a mass, an angular momentum, and electric charge, just certain numbers it has. And it's featureless. A black hole is essentially a featureless object, like an elementary particle, but it can be huge. This black hole can be made in so many ways. Now, the weird thing about that statement is that surely the number of ways you can make a black hole depends on how many different elementary particles there are. You know, if I've got particles A, if I've only got one type of particle, I can make a certain black hole. But if I've got two types of particles, surely there are more ways to make a black hole. So just assigning an entropy of a black hole immediately creates a puzzle. Why are there so many different particles in the standard model? And does the entropy of a black hole depend on how many particles there are? So the answer is, in his calculation, it's one result. You can't adjust it. If you can't change the number of particles. You can't change the entropy by changing the number of particles. It's whatever it is. that actually implies, I believe, that the number of particles in the Standard Model is fixed by gravity. Okay, and we know there are 3 generations of particles, there are 16 particles per generation. That number should be forced on you by the fact that the Standard Model couples to gravity. If it is, then the whole thing is absolutely self-contained, and you just can't separate these puzzles from each other. So particle physicists who are trying to understand how many particles there are in nature, that question's meaningless unless you include gravity. And gravitational theorists trying to understand the entropy of a black hole, that question's meaningless unless you actually use the real number of particles in the world. Okay, so I think that, again, the fact that Stephen's entropy ideas seem to be successful in describing a universe indicates that physics is truly unified, and not adjustable. And so if all of this works, I would say we will be pretty sure that this is the entirety of physics. Because if you add another particle, you're going to spoil all these cancellations and agreements. So that's very exciting, that nature may itself be telling us how things unify. And that all these kind of consistency arguments and arguments about the universe and the Big Bang and consistency with observations may in fact all come together very beautifully into a coherent mathematical picture.
I want to go back to something you said a few minutes ago that I really liked. You said you feel lucky when you work on a theory that can be proven wrong. And yes. I like that because I think it's very different from how many other researchers would feel in that situation. Many others would feel very scared when they think they can just be disproven at any moment with any new data that comes in. Why do you think it's so scary for some people, the thought of being proven wrong?
It's a funny thing, but reality is scary. I don't quite know how to put it, but sometimes when you, for example, just go out into nature, be it a, snowy field in the middle of winter in Canada, or you're hiking in some, tall mountain range or something, or you just look into empty space from Earth, and you think, wow, this is real. That can feel scary. And so reality is scary. And I think it's as simple as saying, I do want physics to be real. And reality is scary. So we just have to face up to that. The way to face up to it is to sort of enjoy this kind of amazing fact that we are able to interact with nature and make sense of it. We don't understand why. We haven't got a clue why we can do that, except perhaps, we've evolved capacities which somehow allow us to do this, but then they go way beyond what we ever needed to survive. So we have a scary capacity. That's obviously true. We can do all kinds of scary things, but I think part of just essentially being a responsible citizen and living up to the opportunity of life, which we all possess as a miracle. We all have this amazing thing called life. And I think just living up to that is facing these scary realities and trying to, deal well with them. I do see this particularly among students, a sort of nervousness, particularly about career. People say, if I work on, a theoretical framework, which may be risky, maybe it's going to be mathematically shown to be wrong. That's probably the more immediate danger, because there's a lot more mathematics than there is physics. So, and there are lots more models of physics than there are real, correct models of physics. So I think for students, sometimes it's more comfortable to work on a model or a mathematical framework, which actually nobody is going to prove wrong anytime soon. But those frameworks, what I would say, are often very unlikely to actually have much to do with reality. And so you may spend, you'll be in a sort of relatively comfortable place, but you'll never experience the magic that the field is capable of. this kind of search for safety is now very common across society. You know, people don't necessarily want to deal with the difficult problems. How do we look after the planet? How do we make sure we're not destroying the environment? How do we reduce inequality? How do we create opportunity for more people to live decent lives and fulfilling lives? On the one hand, you can just sort of stick your head in the sand and say, look, it's not my responsibility. But, you know, I think that's not living up to what the world is offering you and the privilege you have to be part of the world. And you should play a role you should rise to these challenges. So I think this all comes together. I try to encourage young, you know, when you work in physics, a very healthy attitude often is to say, look, I'm going to try something which sounds appealing, exciting. It may be risky, you know, and I'll have a backup plan. If this doesn't work, if it's proven wrong, well, there's so many other wonderful things to do in life. You don't have to follow the conventional path. And if you end up compromising to such an extent, you know, that enables you to follow some conventional path, you know, I feel you're really missing out on the possibilities which life offers.
Have you always had a backup plan in mind throughout your career?
I always did have a backup plan. I think, you know, in my own case, my parents both went to jail for their political beliefs. And then they came out of jail and a few decades later were elected to parliament. And both, so, you know, they had a complete turnaround where their beliefs actually led them into positions of responsibility in government. And so that was very inspiring for me. So I took from them that, you know, one really shouldn't compromise your beliefs. And yes, I had a backup plan. I think even from when I was a graduate student, I was a bit worried about aspects of theoretical physics that I doubted whether these models were actually real. It was kind of a game people were playing, an interesting game, but it somehow didn't really ring true. Grand unified theories or string theories never really felt to me like they were a genuine insight into reality. That's just a feeling, not necessarily one that you should trust. But as a result of that, I basically said to myself, look, if I don't make it in theoretical physics, if I'm not able to make a good contribution, you know, my dream was I would go and be a wildlife warden in a game park in East Africa. That's because I thought there's sort of nothing more fun than sort of looking after lions and antelopes and rhinos in the wild. So yeah, I always had that as a sort of at least a mental backup plan. Mm-hmm. If nobody wants me in physics, you know, I'll go and do something much more exciting. But I'm not. In fact, you know, another sort of strange thing about me is that when I was a postdoc in California, I used to have a recurring sort of nightmare, and the nightmare was that I actually got a faculty position back in my original department in London, that I'd be walking down the corridor and I'd see these names on the doors, and I came to this door and my name was on it, and I woke up, you know, in a cold sweat. Oh no, I'm a faculty member. So the academic career, you know, is not the pinnacle of human experience. You know, I love my colleagues. I like being an academic. I think university is a wonderful place. It's for many reasons, but you should use them to enjoy it and have fun, and, you know, not see that as a goal in itself.
Mm-hmm. As you've said, a lot of these things you're bringing up are topics that I think students struggle a lot with, and you devote a lot of your time to mentoring and giving advice to students, including yesterday you met with a large group of PSI and graduate students here. Yes. And a few of them sent in some questions for you that I'd like to share. So let's start with one from Saba.
I'm Saba, and I'm a PSI student. And before coming to PSI, I was working mostly in cosmology. And then after entering PSI, I got introduced to this whole new ways of doing quantum gravity and quantum foundations. And I decided to somehow work in these directions while I'm in PI, foundational aspects of quantum gravity. And now I'm at the start of my PhD that I'm really trying to figure out whether I should continue working on cosmology like I was doing before, or continue doing this kind of like quantum gravity and foundational aspects of quantum gravity from like quantum information point of view. And at this point, I feel that I found my question. And I think the question for me at the moment is to somehow figure out quantum gravity, problem of quantum gravity. And I don't know what is the most promising avenue to somehow approach the question. Like when we're viewing cosmology, it looks like that at very early point, everything becomes classical, and we don't really know if by studying cosmology, how can I directly address the interest in quantum gravity. And yeah, I just want to know your opinion about what do you think about cosmology in context of quantum gravity? What are the avenues that one can pursue inside cosmology, and what are the most promising ways to somehow do some phenomenological quantum gravity?
Okay, thank you for the wonderful question. I think you are asking the right question. You're recognizing that we're gaining, wonderful insights from observation in cosmology, and you want to apply it to learn something about quantum gravity, which is the big missing component in fundamental physics. The part of the standard model, if you like, that we understand least is quantum gravity. So you're asking the right question. The problem is we don't know the answer yet. And I would say the following, that, the sure bet over the next 10, 20 years is that observations are going to continue to bear fruit. We're going to get more and more precise measurements of the fluctuations coming out of the Big Bang. With that precision, we have much greater power to test theory. So I think that's a very sensible avenue for anyone to take, is to get into data analysis, interaction with observations, modeling the observations, and so on. I think, and I hope many people will go into that direction. Now, I sense from your question that you are more attracted to the more fundamental questions. That's a great thing, but keep in mind that people have not solved this problem for more than 50 years, probably 75 years. People have been trying to solve these problems and failing repeatedly. So the chances of you actually making success are very, very small at best. So what you can do, I think, is pick problems which are instructive, where you are dealing with gravity and sort of refining your understanding of Einstein's theory and of quantum mechanics. If you like, think about it as a musician. We have all these wonderful works by classical composers, and it's great practice, as well as very rewarding, just to sort of review those and give them your own spin and find better ways of explaining them, and so on and so forth. And I think that kind of work is never wasted. So provided you don't expect to really answer, these very, very difficult questions, then I think you will find the work very rewarding. The chances that a solution to this puzzle, will come in the next, I'm very optimistic, the next 10 or 20 years, there will be at least much better resolutions of these puzzles. But the chances are small, and exactly who finds it is a random question. It could be anyone, and probably it'll be somebody unexpected. So it might be, a PhD student somewhere in a very minor institution who comes up with the key idea. That's one of the exciting things about fundamental research. Could be anyone. But if you're in a position where you're studying these questions carefully and rigorously, and you are very critically aware of the different approaches and frameworks, then you'll be in a good position to respond to any such breakthrough which happens. And if a breakthrough does happen, whether it's by you or by anyone else, obviously that's going to blossom into many, many other areas. I mean, if we the second we understand quantum gravity and how it relates to the universe, there will be a huge variety of outcomes and questions and predictions and interpretations. And that's something which, you could easily spend a lifetime working on. So, I would encourage you to go in that direction, study it very carefully, very seriously. Don't put all your bets on one horse, because whatever horse you bet on is unlikely to be the correct approach.
Mm-hmm. And as you said, these breakthroughs can come at any time and
Yes.
from anyone.
Yes.
And I know one thing you were very known for during your time as director at Perimeter was fostering an environment in this academic institution where those breakthroughs could take place.
Yes.
From anyone, not necessarily just from senior faculty members.
Yes.
What do you think are the most essential ingredients that an academic institution needs in order to foster those breakthroughs?
I think it's a recognition that the most likely people to come up with original ideas are the youngest people. And that community of young people. So I see the community of young people as the most important in the Institute. Don't get big-headed, those young people watching this. But I do see that. And I think, furthermore, they need to be very diverse. I think diversity is very often a source of strength and enthusiasm. And, difference is very, not just, it encourages new ways of thinking. It's a commonplace, but very often in physics, the best new ideas come about when two different strands of thought collide and suddenly realize that the other one has some insight they can benefit from. The Higgs mechanism in the Higgs boson is a classic example where Peter Higgs was aware of ideas happening in superconductivity, which were by and large ignored by particle physicists, mainly because the particle physicists were fairly arrogant and they couldn't possibly believe that somebody studying materials, could actually give them a real insight. But Higgs grabbed that insight and interpreted it in terms of, and incorporated into particle physics. And that was extremely profound and important development. Although, initially it was resisted. People didn't believe what he was doing at all for several years. So I think diversity of different types of people from different countries, from different cultures, especially gender diversity is really important among that young physics community. And it should be an environment. I think another very important thing is that the people who often are most original are very often odd in certain respects. They are unusual people, and they're not necessarily very good at coping with, the everyday rigors of life. And so it's very important that any community which fosters talent be specially supportive of people who are unusual in whatever respect. So I think that's essential. And again, by supporting unusual people, different people, that's probably the best way of ensuring the field isn't a monoculture, all pursuing the same direction, which as I've already expressed, the most popular directions haven't panned out in the last 40 years. And that's reason why we should make sure we pursue a real diversity of directions.
Now, I want to ask you more about these unusual people and how you find them. But first, maybe let's just go to one more question sent in from a student. This one was sent in from Vatsalya, who's a PSI student. Mm-hmm. And he wrote in asking, do you think that as theoretical physicists, it is our moral responsibility to pursue research that explains the real world? Or is it okay to just enjoy playing with mathematical structures? Yeah,
that's a difficult question. I do think I I think above all that theoretical physics is very hard. And it's very hard it's a kind of torture. We do these very difficult, complicated calculations, and they take days or weeks or months. And sometimes you just end up with a paradox and confusion. So it's not an easy life choice, but somehow we do enjoy it. And so I think in order to make sense of why we enjoy it, it's quite good to have at least some idea why, some idea of our motivation. I've met a lot of theoretical physicists who like nothing more than making diagrams. And they say, they like writing papers because it's a chance to make a diagram that they can put in the paper. But the part of it they actually enjoy is making the diagram. So, people do it for all kinds of reasons. I don't think there's much of a moral responsibility. I see it more as a responsibility to yourself. Don't delude yourself. I guess that would be my overriding message is if you like playing with mathematical frameworks and if you're good at it, then by all means do it, because the work you do will be good and other people will may well draw some interesting physical conclusions, even if your work is just mathematical. So I would never denigrate anyone for doing something they enjoy, especially when they're doing it well. Even if it doesn't directly relate to physics, it's more like playing a game, a mathematical game. I think, that's fine to do. But as I say, I in a certain sense feel sorry for them because I think the real magic of physics is that these mathematical considerations end up connecting with reality. That's the deep mystery of the field. Somebody said this to me a few days ago. Mathematicians make their frameworks and do their calculations, but physicists somehow have a direct line to God. Okay. Now, I don't believe in God. I'm not religious, at least not in any organized sense. But I think there's a kind of element of truth in that somehow physicists have uncovered a fundamental feature of existence, which is this strange ability of our minds to really make sense of what's around us. It's a very deep puzzle, and I think, if you like, the best way we can appreciate that puzzle and further it and pay it homage almost is to practice that, to make sure what we do does, or to try to relate the mathematics we do to the real world.
Mm-hmm. In many ways, you're speaking to this idea that physics needs many different people, including people who like to make diagrams, or maybe people who might be considered unusual.
Yes, absolutely.
Maybe another way to say it is people that don't necessarily succeed in the traditional academic hierarchy that we've constructed. So I guess as a director, it must have been very challenging to find the right people, because you probably couldn't just look at the applications they submitted, which are maybe trying to show you other metrics than the ones you would want. So how did you go about finding the right people?
Yeah, so I think that this was something I'm particularly proud of as director, is that, when I came to Perimeter, the faculty was very small, and it wasn't really structured at all, and it wasn't clear how it should be structured. The government and supporters had made big investments in Perimeter, and it was very important those paid off, in the sense that the Institute actually did good work and it became recognized as a place, where excellent theoretical physics was done. So it was quite a challenge, and I think I took the point of view that we needed very rare people here. There was nothing stopping us from recruiting from all over the world, and we needed to look as widely as possible and sort of keep our eyes and ears open for unusual people who'd done something unexpected. So it wasn't a matter of reading applications or, it was really being proactive. I also learned that the senior physicists who were advising us weren't always, or even often, the best source of ideas as to who to hire, because usually they had their own field and their own visibility, region that was visible to them was very limited. And secondly, if they saw somebody really good, they thought was really good, they would try and hire them themselves and not recommend them to us. So that was interesting. So I think the short answer was just by really keeping eyes and ears open and looking for very unusual people who maybe had unconventional career paths. And then imagine what would happen is when you hired them, if you gave them much more freedom than are usually given to young faculty. So one of the rules we introduced is that as a young faculty member, you should not spend more than 20% of your time on administrative duties. So that includes teaching, mentoring, applying for grants. And that's extremely unusual because most universities, when a young faculty member arrives, they're immediately loaded with teaching and grant applications, and they very often judged on their success in winning grants. And I think that's very antithetical to pursuing original research. So I would always tell the young faculty, go after some problem that really fascinates you. If you don't publish anything for 2-3 years, it's no problem. You will explain to us that I went after this very difficult problem, and we will all respect you for that. We're investing in you because we think you have the capability of doing something unusual, and so please go after something unusual. And of course, we will advise you and try to make sure you do enough to keep your career going. But it should be a much more sort of supportive framework than is usually provided to young faculty in universities. Mm-hmm. So I see it, the job of a institution is more to challenge people to really be adventurous and ambitious rather than to judge them all the time, and particularly on criteria like publications, citations, conference talks given, and all that. These are really the sort of these are more the symptoms of physics. They're not the essence of what we're trying to do. So in many ways, I try to set an example where Perimeter used very different metrics to judge people. I think metrics like how creative are they, how stimulating are they to have around? Do they have original ideas? Do they question things? Are they asking good questions? Those characteristics of people are actually much more important than the more conventional measures of success.
It seems like it really involves looking at the institute as a whole, rather than just evaluating whether each individual person is successful.
Yes, one of the biggest diseases of the academic model, particularly in North America, is the idea that every researcher has a grant and they use the grant to support their postdocs and their students. So what you're doing is deliberately putting individual researchers in competition with one another and deliberately creating hierarchies. And I see this everywhere. It's also become increasingly common in Europe and elsewhere, I'm sure. And I think this model of the single investigator at the top of a pyramid is actually very destructive of creativity, originality, questioning. Because the more junior people don't want to question the senior person who holds the cash. And I think that's the wrong way to do things. I much prefer a much flatter structure. And actually, conceptually, I think a much better picture is an inverted pyramid, where the senior people, if you like, are at the bottom, and their job is precisely to support the younger people. And, the flowers on the tree, they can be the root, but the flowers on the tree are the young people, and that's really where the emphasis should be.
it seems like a lot of the things you would ideally look for, like being creative, asking good questions, are things that are maybe more difficult to measure or difficult to predict ahead of time. So I guess another essential ingredient is maybe being okay with taking risks. And so I'm just wondering if that's true. Is it important to kind of embrace the fact that some of those choices you make might not work out?
Very much so. As I say, when I talk to students today, I'm very often struck by, they say, well, I'd like to do something more exciting and more interesting, but it would be risky. And yeah, I find that very disappointing that people, I understand it, they need to ultimately make a living. And young people today are, as a sort of, as a generality, young people today are much less secure than they were in my day as a student, where I think we felt that sort of if for whatever reason things don't work out, there are plenty of alternative options. And we weren't nervous about livelihoods in the same way. There are very good economic reasons for that. The ability to find jobs is certainly more difficult today than it was several decades ago. And even my generation, it was much harder than it was in previous generations. Previously, universities were really, or at least advanced research was the privilege of a very small number of people. And as a result, they had much greater job security and didn't really worry about getting academic positions. So my professors never really worried about this at all. I didn't have to get grants. Money was more or less just provided in the 60s. So the climate of the field has changed. Part of that has been letting larger numbers in to the field, which is a good thing. Widening access means greater pool of talent, and things should move faster. But what has come along with that is much more standardization and prescription, telling young people you've got to do ABC to get a job. And I think that's that's been damaging. And I see this all across higher education, actually, is that the quality of degrees now being awarded, I don't think is what it should be. Even if you look at undergrad degrees, the curriculum has become very standardized and rather dull, and initiative is not rewarded. So this is not in isolation, it's everywhere. This sort of massification and then standardization and loss of creativity. So theoretical physics is very fortunate because it's such a cheap field. We just need a blackboard and chalk and occasionally a computer. It's really a very cheap field. So if anybody is going to recreate, the organization of science more optimally, it has to be theoretical physics. We have one of the most effective of all sciences, if not the most effective in terms of predictions. Theoretical physics, can't be matched. We have the cheapest. We have the easiest, the most universal, easiest to access. You don't need a lab. You can come to a summer school and learn some ideas, and they may enable you to write a very interesting paper. So theoretical physics should be setting the example for the rest of science. So it's very, very important that we strategize our field carefully and wisely. And I don't think that's happening in general.
Mm-hmm. You've also said in many ways that diversity is a very important ingredient. And it just reminds me of something that I noted down that you said yesterday when you were meeting with students that I really like. You said, theoretical physics is special because it's cross-cultural and everyone has the same questions.
Yes.
And so I just wanted to ask you, because you have throughout your career traveled all around the world, met with researchers at every level and from everywhere. Yes. What do you think are those questions that everyone is asking?
Well, I was very struck, for example, I'll tell you one little story. So I was in Senegal and I was teaching electromagnetism relativity, and there was a student who had done maths at university, so not physics, and it was kind of a lively student, So I asked the whole class, when I started the course, what would you like to be? And his answer was, a billionaire. Okay, which actually, you can say it's kind of crass, but compared to the other students who largely said, I want to be a professor, I found it more exciting to have somebody who's at least not just saying, I want to repeat, exactly what the people who taught me and so on. Anyway, so he wanted to be a billionaire. So we started chatting, and then he was very puzzled by physics. What is all this stuff? You keep referring to reality and light and all that, and you're writing down some equations and so on. So then we had, at some point, an interaction about the problem sheets. And at some point, it involved instabilities. And at some point, I was trying to explain what this instability was. And at some point, he said to me, "Oh, you mean physics is just logic?" And I said, "Yes, that's exactly what it is. It's logic applied to nature." He said, now I get it, right? And then he got very interested. And then in subsequent days, and this is the wonderful thing about meeting someone from a completely different culture and background, academically, as well as, culturally and linguistically, everything. He started to say, gosh, you can apply logic to the real world. And then he, naturally, what do? You point to the stars. And in Senegal, where we were, it was in a nature reserve. It was actually a wonderful place. And there's this huge open sky with the stars. And you immediately say, what are those? What's the logical basis of stars? And then that was an excuse to have a conversation about how stars form and how they work and nuclear physics and so on. And so, yes, people very naturally ask the same questions. It's because we all live in the same universe and we're all sort of puzzled and amazed by the same natural phenomena. And so that is the cultural unifier. When it is the realization that the phenomena which are just around us all the time and which are miraculous in various ways, that we can share this. We all do share it, and we can discuss with each other and share our understanding of how that works. And that somehow gives you a grip on the world, which you share. And I do think also it makes you feel more responsible and more empowered. If you understand the world, you're certainly much more empowered than if you're just kind of at its mercy. And so I think this understanding between different cultures, different peoples, fundamental understanding of the world is very empowering, is very unifying. It makes us all feel, we're part of the same enterprise. And so that's really the most exciting thing of all.
Definitely. Well, Neil, thank you so much for this amazing conversation. It's been so much fun to talk to you. Thank you.
Thank you very much.